Good morning, Zamfam. This is your AP instructor, Mr. Kennedy. We're going to go through two problems today. Both are sort of short. You'd probably like to get either of these problems. I think they're on the easier range. They are problem from 2002, M3, and from 2003, M1. So I think I emailed you or put on Google Classroom these two problems. So let's take a look. First one is an energy function. Ooh, energy function. Let's get set up here with the old handy American Girl doll, fancy stand. Okay, I'll take this down. You can do it. Wonder Woman says you can do it. Let's see what we got here. All right, so I want you to sketch a graph. So I sort of overdid it. Made a table just with integer values for x, and you get these values for y or u sub x. The energy when we're moving away seems to be going down, an inverse relationship. There's the equation we use. We sketch those points. And we got an inverse curve there. That's all they wanted for that one. Pretty easy. Then they want to know the force. So this is the equation that's actually not on the equation sheet that you should put in your back pocket. If you have an energy function, if you take the derivative of that energy function, it'll give you the negative force. Sort of bizarre idea, but you can almost think, remember we had a marble on this roller coaster track. The force or the acceleration of that marble is going to be the opposite of this slope. Okay, so what do? We place that 2 plus x up top and put a -1 there, and then we just say, hey, the derivative of that is going to be this to the -2 power, and chuck a negative over there. So there is our derivative function. If force is equal, a negative force is equal to that derivative function, then we just say, hey, get rid of that negative, make it a positive. So we end up with the force acting on this object to be 4 over the quantity 2 plus x squared. All right, A and B, pretty doable. C, CS4. Just ask for the speed, the velocity of this sucker if it starts from rest. So starts from rest, wants to know the velocity at a point. All right, before we were given the energy function and also the force we figured out. Ooh, if we have energy, and we want to get velocity, we should always be thinking, I bet we can use law of conservation of energy. The fact that energy cannot be created or destroyed, but can be transferred. So we set up our energy conservation equation. U sub I plus the kinetic energy initial is equal to the final potential and final kinetic. We don't have any kinetic energy because it starts from rest. We do have some potential energy, 2 joules, and that goes down to 1 when we get to 0.2 meters. So then we just solve for V. And we get 2 meters per second. Piece of cake. D and E are more experimental, so you got to think a little bit. How could you actually prove that this is the case when you have this glider? So there's multiple ways of doing that. The easiest and the one that students most use is they just say, hey, I'll measure out to 2 meters on this track. I'll put a photo gate slightly before, slightly after. I'll measure that distance, that delta x. From the photo gates, I can get a delta t, and I can get that technically average velocity, but it can be pretty close to instantaneous, and I'll compare that to the function's value, or what I claim that velocity value is going to be. All right, and for that you need a meter stick and 2 photogates. There's other ones you can do with springs, there's other ones you can do with projectiles, creative, but this is the most common one. Okay. 2003, I think, I actually might have given this to you early. Can you remember way back when life was normal in September? This might have been one of your exam questions. Way back September, October. Who would have thought that we'd be in this predicament back then? Oh, I digress. So we got a position function of x is equal to 0.5 t cubed plus 2t. If we want the velocity and we're given a position function, we just take the derivative of that function to get our velocity. So 1.5 t squared plus 2 is our velocity. If we want a velocity at time 0, we just chuck in a 0, and we got 2 meters per second. Fantastic. Then they ask for the kinetic energy. Well, kinetic energy is just 1/2 mv squared, but we want it in terms of t. So if we can define v in terms of t, we can just chuck it on in there. And yes,
is my coffee down here?
Making a video. You're interrupting physics right now. I'm sorry, she just doesn't understand.
What is this?
Yes, no, that's my coffee. Any chance you bring it up to me? No chance. Okay. I'm sorry about that. So kinetic energy, there you go, there's your equation. We plug in the velocity function that's in terms of t. Wonderful. Half of the mass, they give you the mass, is 100, so that's just going to be 50. So there's our kinetic energy function. Voila. They want a force function. Well, to get a force function, we would need to know, we already have mass, we need to know the acceleration in terms of time. So back up here, take the derivative of that velocity function, we get acceleration. So what is that? 1.5 times 2 gives us 3. 3t is our acceleration function. Beauty. And then we chuck in 3t there, times 100 kilograms. We get our, if we want our force acting on this object, just multiply t by 300. Bada bing, bada boom. Power, same way. To get power, shortcut is force times velocity. Power is also work divided by time. So if we just take those two functions and multiply them together, we can get power in terms of time. This becomes some sort of cubic. You can leave it that way or multiply it out if you wish. I'll leave that for a second. All right, what do they want next? Work. Work done on the box between 0 and 2. All right, 2 ways to do that. We could just say, what is the change in kinetic energy? That's probably the easier way. Again, we should have this one in our pocket. Is that on the blue sheet? I forget. Maybe it is, maybe it's not. I don't think it is. I'm not sure. Check. So we just subtract those starting and finishing kinetic energies. The kinetic energy at 2 meters, well, the velocity is 8 meters per second. So we chuck that in there, we square it, and at 0 meters, the velocity is 2 meters per second. We already figured that out, we square that. Once we do all that math, we get the difference of those two is to have 3,000 joules added to the system. So yeah, we must be speeding that sucker up, doing some work on the system, because now it has 3,000 joules, where it started with, whatever that is, 4 times 50. I'm not going to do math this early in the morning. We could also do it the fancy way. It takes a little bit more. At least you can flex your calculus muscles. Work is also the integral of the power function in terms of t. So that power function was those two velocity, actually, and force functions. If we multiply those out, we get 450t cubed plus 600t. All right, that's our function that we got to integrate from 0 to 2. All right, there's the integrand. Did I say that right? And then we go from 0 to 2. Well, 0 is not going to give you all that much. It just becomes 0. So we chuck in good old 2 in there, and we get 3,000 joules. Amazing. Cool. And lastly, we're going to keep this under 11 minutes. That person has to both do work on the box and has to, some of its energy gets sucked away from friction. So it asks for what? Indicate below whether work done on the box by the student in the interval 0 to 2 would be greater than, less than, or equal to the answer in part C. It's going to be greater than. That person has to do some work on the box and has to do some work to overcome friction. All right, peeps. Eat your vitamins. Say your prayers. Be a Hulkamania. Maniac. Until next time. Like, subscribe, retweet, press that button. Keep an eye out for the Codemaster or Breaker, whatever they are. Sam Fam out.